Okay, let's get started. Um, so recall we had like several, important results. I guess from previous times. So we had the result that uh, a principal ideal. So let me just remind you: a principal ideal A of a ring R um, uh, is of the form, right? It's of the form like they call it bracket A, or sometimes like this, right? Or they denote it AR or RA. But normally we're working with commutative rings. So this is the setup AR such that R is an R, right? Where here I'm multiplying. So it turns out like you can use division algorithm, but the idea is that um, uh, the ring f of x, right, for f of field, f a field, the all ideals are, let me just say all ideals are principal. So this is going to come into play later on. I mean, actually today, but yeah. So another one of the main theorems we'll use is theorem. It's the fact that an ideal p of x, right, not equal to the zero ideal, and f of x is maximal if and only if p of x irreducible over f. So from this, now you know how to make new fields, right? So you just take f of x, right? And then you quotient out by an irreducible polynomial. And then boom, you have a new field. So the next goal is to study like what are these fields, right? Like how can we describe them? So yeah, is everyone clear on where we're going? So we're going to basically be using this theorem a lot, right? We're going to quotient out by an irreducible, get a field, figure out what kind of field that is. Everyone good? Okay. So let's define something first, right? A field E is an extension field of F if you know they're subsets of each other. So if F is a subset of E. Okay. So let's sort of think about what these terms are, right? Uh so let's, in general, right? In general, let f of x be irreducible polynomial over f of x. Then if we quotient this out, right? Since this is irreducible using right here, right? Using the thing here. Oh, by the way, when I write f, it's a field. Yeah. But since it's irreducible, it's maximal. So I know this is a field, but it's not just any field, right? It's a field that has a root of f of x. Yeah. So what do I mean by this? Well, let me just give you an example, right? Like let's take q of x, and then I quotient out by x squared minus 2, right? So can anyone tell me what all these elements are? Like how do you describe this field? Like what are the elements? No. I mean, there's no, like just by definition, what are the elements here? Like x squared minus 2 is 0, right? So what is x squared? X squared is 2, right? So do you all agree? Again, I can reduce every high degree polynomial to either a linear or constant term, right? Because x squared plus, I don't know, x cubed plus x squared plus x. Let's just do an example again, right? X squared is 2 because x squared minus 2 is 0. So this is x squared times x plus x squared plus x plus 1. On the other hand, x squared is 2, so this is 2x plus 2 plus x plus 1. So this is the same class as 3x plus 3. Yeah, so do you all agree, like, every element here is, like, of the form ax plus b, where ab is in q? I'll say class, yeah. Just but we normally don't write class here, okay, like sort of understood, but because I mean I don't want to be putting brackets over everything. It looks ugly. So does everyone understand this? Yes? No? Oh, you're close. So it's not reals, but it's isomorphic to like q adjoin a real number. But from here, it has a root. I'm gonna use a different variable of t squared minus 2, right? Of this polynomial. Namely, the root is x. Yeah. And certainly the element x is in here, right? X is a root of the polynomial t squared minus 2, because when you plug in x in, well, x squared minus 2 is 0, right? From this condition. So it has a root of, whatever you model by, right? So that's sort of the idea. I'll I didn't I don't think the professor went over this, but you can check that, this thing, right? We're adjoining a root of x squared minus 2, so that's root 2, right? So the idea is, like, this is isomorphic to q adjoin root 2, which is this is the set of a plus b root 2 such that ab is in q. So we got a bigger field, um, from the smaller one. So it's isomorphic because, we send a plus ax plus b to I don't like this. It should have been, how about I write just the match notation, bx plus a. Yeah, so I send bx plus a to b root 2 plus a. Yeah, and it's well defined because root 2 squared minus 2 is 0. Yeah. So so these two are sort of like isomorphic. So that's the idea. Yeah. So we're sort of, by quotienting, we are sort of like adjoining a root of the polynomial. But that's for later. Yeah, this is later. He didn't really go over simple extensions yet. But is everyone clear on this? Yes? No? Does everyone follow? Okay. So uh, let's go over something he did go over. So now we should, now that you see this, you sort of see why it makes sense to define algebraic elements, right? Those elements that are roots of polynomials, right? So in general, because that will be pretty much what we adjoin. So in general, an element alpha of extension field E of F is algebraic over F if F of alpha is 0 for some non-zero f of x in f of x. Yeah. So and then if alpha is not algebraic, we just give it a name. So we call it algebraic over f, sorry. Over f, then alpha is transcendental. I don't know how to spell that. Transcendental. Right? So the like the element square root of 2 that I showed you before, this is algebraic, right? Because x squared minus 2 is 0. Right? It's a root of this, right? So I'm taking f of x to be this. So it's a root of that. So these are algebraic elements, right? So so you can see that a field, right? So we could sort of adjoin Q with these. The idea is later on you'll be adjoining Q with algebraic elements, and then we relate that to quotienting by ideals, pretty much. And then just this for an arbitrary field, we say an element C that is algebraic over Q. So this is when the specific fields are C and Q, an algebraic number. And then a number in C transcendental over Q over Q is a transcendental number. So in general, it's hard to prove a number is transcendental, right? So that would require some huge theorem, or like, because you can imagine, right? So I can tell you, I'll tell you now that like pi is transcendental over like Q, so transcendental, but it's hard to prove, right? Like you would have to prove there's no polynomial. You have to prove, there is no polynomial. I mean, prove directly, right? Prove there is no polynomial in Q of X that has pi as a root, right? Because again, the naive way doesn't work, right? This thing has pi as a root, but it's not in Q of X, right? Because pi is not in Q. Does everyone understand? Yes. No. Like, I'm just saying, to prove pi is transcendental, you would have to prove this, and that's very hard. Like, because you have to show you have to show no such polynomial exists, right? But there's like infinitely many polynomials, right? There's like degree 100, 301, right? So like, and I'm just saying, like, people might ask, what about this one? Well, this one does have pi as a root, but it's not an element of Q of X, right? So yeah. Okay. So from here, you can ask, right? Like, an algebraic element has a polynomial as a root, but there are many polynomials that have. If I say you give me a polynomial that has 1 as a root, you would tell me like a lot, right? Like there's many, right? Like x minus 1, x minus 1 squared, x minus 1 times x minus 2, right? There's a lot, right? So the next thing you should ask is there a smallest one? And there is. So theorem, let E be extension field of F and alpha is in E, alpha algebraic over F, then there exists irreducible polynomial P of X in E of X, or F of X, sorry, in F of X, such that P of alpha is 0. And the important thing is the irreducible polynomial is unique up to constants, up to constant factor in F. Yeah. And is a polynomial of minimal degree greater than or equal to 1 in F of X. Right? So there's like a smallest one, right? That's what the minimal degree is, right? There's like a smallest one that has whatever as a root, right? So, right? So what do you mean by minimal? Well, if F of alpha is 0, right, for F of X in F of X, then P of X divides it. Yeah, that's what we mean by minimal. Yeah. So if you have another polynomial that has alpha as a root, then this irreducible one must, divide it. So since it's irreducible up to constant, then we can just factor the constant out to make the thing monic. So, so without loss of generality, assume it's monic. Right. So let me just remind you, like, this is actually the crux theorem here. So the main theorem. So why is this true? Well, you could define a map from f of x to e, given by you send f of x to f of alpha, right? This is some element in e, and the kernel is precisely, functions with alpha as root, right? Yeah, kernel of phi, if you like. But from here, right? Wait, let me underline it. Right here, right? In a ring f of x, f of field, all ideals are principal. The kernel is always an ideal. So this thing is always, so the idea is that this thing is always principal. So it's generated by like one element. So if you like, it's generated by P of X, since they didn't know it as P of X. Some books will write it like this. Some books will write it like this. I mean, either way, it's the set of P of X, G of X, such that G of X is in F of X. Yeah, it's a principal ideal. And that's pretty much what you take to be your irreducible one, right? It has to be the smallest one, right? Because if there was something smaller, then it wouldn't be P of X wouldn't generate everything, right? So the fact P of X was principal, was your principal generator, sort of shows that this is So basically everything is in this kernel, right? So if so the last statement follows, because if f of alpha is 0, f of x is in the kernel, right? And the kernel is generated by this thing. But what's the definition? This thing is the set of p of x, g of x, such that g of x is in f of x, right? So by definition, if you belong to this set, then f of x equals p of x times, let's call it like g prime of x, right? For some g prime. And that precisely means that this divides this, right? So the last statement is clear once you just by definition. Is everyone good on this? Well, we'll do examples soon. So yes, no. Okay, sure. So before that, let me just give one more definition. Let E be an extension field of F, alpha in E algebraic. So normally we'll be caring more about algebraic stuff over transcendental. So the unique monic, irreducible polynomial that I just talked about before, polynomial, like the generator of the kernel, in theorem is denoted, the book denotes it irreducible polynomial of alpha over f. Yeah, that's how you read it. So it's the irreducible polynomial of the element alpha over the field f, right? And the degree of this irreducible polynomial is the degree of, is the degree of alpha over f. Okay. So let's do examples, yeah? So I'm sure that's what you all want. So example, let's go over algebraic numbers, right? Let's show alpha in C is algebraic over Q. So let's do part 1, right? 1 plus root 2. So how would you show this element is algebraic? Good. Does anyone have any idea? So let me go back to the definition of algebraic. So where is it? So again, your algebraic, if you could find some polynomial that has a root, right? That has that number as a root in this case. So here it's asking, find a polynomial over Q, right? Because it's over Q in Q of X that has 1 plus root 2 as a root. So in general, like if I gave you a polynomial and asked you to find the roots, it's easy. I mean, it's hard. Yeah. Here, it's a bit easier because what you can do is, here's the trick, right? Let alpha be whatever, and then just solve for it. So, get rid of the square roots, right? So how am I going to get rid of the square root and the root 2? Well, let's move 1 to the other side and then square, right? So I get alpha minus 1 is 2, right? So I square both sides. Now this is alpha squared minus, was that 2 alpha? Did this correctly? 2 alpha plus 1. So alpha squared minus 2 alpha minus 1 is 0. So what is 1 plus root 2 a root of? What polynomial? Come on. I wrote it down. It's like right in front of you. uh, buddy, this should be easy at this point, right? I mean, alpha is a root of. I just have something where I plug in alpha and I got 0, right? So it's the root of this, right? Sorry. So alpha is root of. Yeah. Because what does it mean to be root of? It means if I plug in, I get 0, right? And that's exactly like what happened. So but alpha was just this element, right? Alpha was 1 plus root 2. So 1 plus root 2 algebraic. Is everyone clear on this? I feel you all look confused. I mean, not look, but from like the lack of response, it seems it's confusing. Or yeah. So I mean, this is how I would do it. I mean, 1 plus root 2 is easy enough to the point where you could probably, what do you call it, brute force, right? But this is like more explicit. So how about next question? Let's do more practice since you all seem not confident. So root 2 plus root 3. Show this is algebraic. Yeah. So same exact thing. Yeah. I'm going to do the same exact thing. So there are 2 square roots. So let's get rid of one of them, right? So let's get rid of the root 3, right? So let's square both sides. So now alpha is what? What is this? Alpha squared minus. Tell me if I made an algebra error, by the way. I think it's 2 root 2 alpha, right? Okay, and then plus 2 is 3, right? So now this still isn't, in Q, right? Again, I'm getting rid of the square roots because I want to be in, Q of X, right? The rational numbers don't have square roots, so I need to get rid of it. So now I need to get rid of the root 2 here. So let's move the negative alpha to the other side. So I get negative 2 root 2 alpha equals, so 3 minus 2 is 1 minus alpha squared. And then let's square both sides, yeah? So square both sides. So what do I get? What's 2 root 2 squared? That's 8, right? 8 alpha squared. Sorry, bad with algebra. So 8 alpha squared is 1 minus 2 alpha squared plus alpha to the 4th, right? So if I subtract 8 alpha squared, you see alpha to the 4th minus 10 alpha squared plus 1 is 0, right? So alpha root of x to the 4th minus 10x squared plus 1. So root 2 plus root 3 is algebraic. Is everyone clear on this? At least how to do these problems? Okay. Let's move on to something new. So let's move on to, I mean, this only works with like stuff with square roots in them, right? Like, I mean, it probably won't work for like, like if I gave you like show I is algebraic. right? You wouldn't let alpha equal. I mean, I guess I guess it will work for this, but I mean, you know, uh, let me think. Mm, well, mm, I don't know if it will always. I mean, you're not gonna do this if how do I say it? You might want like a different argument, I guess, if it's like so later on, like if I gave you like 100th root of 2 plus I, yeah, you're you're not gonna, you know, take 100th powers, right? Like you're not this is like ridiculous, right? Like 100 equals 2, right? If I subtract I on both sides, like I mean, like yeah, but like it doesn't seem reasonable. I guess is what I want to say. So like, um, you want like better arguments than this. So yeah, so later on there you'll learn more tools for like easier arguments than this. But okay, anyhow, let's continue. So yeah, I'm very iffy on always because when someone asks always, it's like, you know, I never want to say always. uh alpha q and degree. So here, right? So before the previous questions, it was just find a polynomial, right? That has whatever number as a root. But now this is asking find the smallest one. Yeah. So let's do an example. Yeah. So like let's do root 3 minus root 6, right? So let's same procedure, right? For now. Alpha squared equals 3 minus root 6. Alpha squared minus 3 is negative root 6. Square both sides. Minus 3. Alpha squared minus 3 equals 6, right? So what is this? Alpha to the 4th minus 6 alpha squared. What is that? Plus 9, 6. Alpha squared plus 3 is 0, right? So alpha root of x to the 4th minus 6x squared plus 3. Okay, everyone follows so far. So now the question is this thing equal to irreducible alpha q, right? So all I did was show this thing has root 3 minus root parenthesis 3 minus root 6 as a root, right? I don't know if it's the smallest one. So does everyone agree? All all I have to do is show this thing is irreducible. Yeah. Does everyone see why I'm done after this? After I show it's irreducible. Yeah. So yeah, I mean, because it's by the uniqueness of that theorem, right? So all we need to do is show it's irreducible. That's sort of why we went over irreducibility and polynomial rings before going over fields. So you have tools to show this irreducible, right? So let's assume it's reducible. Then it will either factor as degree 1 and 3, right? I mean, it could be, you know, like it could be 1 1 1 1, but like we could just combine the other 3 1s. So it's either 1 and 3 or 2 and 2, right? Does everyone agree? Because it's degree 4. So what are the ways to like go degree 4? So um, you see, in this case, it's very annoying to argue this case by case, right? So in this case, I'm telling you, you could argue like it can't be this, it can't be this, explicitly, but I'm saying there's an easier way. What's the easier way? You learn something that tells you this polynomial is irreducible. What is it? Yeah, Einstein with what prime? So I'm saying just ignore this. Easier. Yeah, so I think it's Eisenstein, right? Not Einstein or Eisenstein, or I forgot. Eisenstein with p equals 3, right? So by this thing is irreducible. So we are done. Everyone clear on this? So it could have been reducible, right? I'm not saying it doesn't. So it's possible, right? It's possible this thing isn't the smallest one, right? It's possible. Like I'm not saying it's always the case that it's irreducible. But the reason I wrote this is because I noticed Eisenstein. But it's possible it could reduce. Okay, let's continue. Let's do one more. Oh, by the way, I didn't really answer the question, right? So the degree is 4. Yeah, the degree is just the degree of the irreducible thing. So it's 4. Okay, so continuing on, let's do one more, and then we might call it a day. So root 2 plus I. Yeah, you want to use the alpha thing, right? Because how do I say it? Like this thing. So let's do alpha equals root 2 plus I. So this gets a bit more tricky, right? So let's get rid of the root 2 first. So alpha minus I is 2, right? So I squared both sides. And then alpha squared minus 2I alpha. So I squared is -1, right? So now I need to get rid of the I. So that's easy. I just need to square it, right? Because I squared is -1. So let's move the alpha squared to the other side and 1 to the other side. So 2I alpha equals 3 minus alpha squared. So let's square both sides now. So I get 4. No, I squared is -1. So -4 alpha squared equals 3 minus alpha squared, 3 minus alpha squared. So tell me if I made an algebra error. So I get, but I mean, this thing is what? 9 minus 6 alpha squared plus alpha to the 4th. So I get alpha to the 4th minus 2 alpha squared plus 9 is 0. Yeah. So alpha root of So I'm doing this because to tell you, so it's not always the case that Eisenstein works, right? So here's an example of one. Yeah. So this one, you have to. There's no way around it. Yeah. This is something you have to do. You have to argue. It can't be reducible case by case. Yeah. So assume x to the 4th minus 2x squared plus 9 reducible. Yeah, so the first case is degree 1 and 3, right? But what does degree 1 mean? Can anyone tell me? Like, if it splits to degree 1 in Q of X, what does that mean? Like, what's that theorem you learned? It's like, if X minus alpha is a factor, what is alpha? It's a root, right? So degree 1, if it splits to a degree 1, that would mean there's a root in Q here, right? So here, I'll let you do this for practice. I don't think it's that hard. Rational root theorem. You all know this, right? So just plug it in, check to check there are no roots. Check no roots in Q. Because I think what are the factors? Is plus or minus 3, right? And since you're squaring everything, minus 3 and plus 3 get the same thing. And like plus 3 to the 4th is like what already? I think it's, yeah, it's already like 81, right? There's no way it's gonna be 0. So use rational root theorem for no roots in Q. And now here comes the annoying part. Yeah. Is everyone good? Can I erase like everything from here to here just so I could keep the same page? Is everyone good on this? Okay. So now we argue it can't be degree 2 or degree times degree 2, right? So I'll just write 2, 2. Yeah. So is everyone clear that we could assume it's monic? Yeah. Because if I had something like this, dx squared plus ex plus f, from the fact that the x to the 4th term has a 1 in it, do you all agree a and d have to be inverses to each other? Yeah, so I could just factor it out, right? And then consider BA inverse x plus CA inverse. And then times x squared plus ED inverse x plus FD inverse, right? And then these are inverses to each other. So this is just 1. So is everyone clear? I could reduce to the case where it's x squared plus, ax plus b times x squared plus cx plus d. Everyone clear? So I can assume it's monic. Yeah. So now the question is there a b c d such that this these two multiply to x to the 4th minus 2x squared plus 9. So does everyone understand what I'm doing right now? So I'm sort of trying to see if it could split into 2 degree 2s. In this case, 2 monic degree 2s. Okay, well, there's no helping. You have to argue. So let's see. Yeah. So from the constant term, right? The constant term is BD, right? And it has to match the constant term here. So BD must be 9 always, right? So, and always, if I match the x cubed term, what is the x cubed term? It's C plus A, right? And that has to be 0. So A must be negative C. Everyone agree? So this is from x cubed term. This is from constant term. Yeah, come in. X cubed term, that there's like no x cubed term, right? So if you match the x cubed term, you must get 0. And similarly, the x term is AD plus BC, right? I believe, right? AD plus BC. And that also has to be 0. Everyone follow? Okay, well, I mean, here there's no helping it. So from let's consider the first case where I mean b is plus minus 3, d is plus minus 3, right? And make sure when you write this, if it was negative 9, you would do b plus minus 3 and d minus plus 3, yeah? So by plus minus, since the plus is on the same spot, it means that if b is 3, d is also 3. And if b is negative 3, d is negative 3, right? So from here, right, what do we get from the x term, right? From here, I get that since they must be the same, 3a plus 3c is 0, right? So what do we get? Does that tell me anything new? No, it doesn't. So from here, so I guess it is possible. So I guess from here it tells me nothing. uh, so let's, okay, so now we go to the x squared term, right? So what's the x squared term? It's, what is it? D plus b plus ac, right? No, it's negative 2, sorry. Yeah. So a must be negative c. So this is d plus b plus negative c squared is negative 2. Now d plus b is 3 or minus 3, right? So let's consider the case where they're 3. They're both 3. If they're both 3, then it's 6 minus c squared is negative 2. Negative 6 minus 6 minus 8, right? So c squared is 8. So this can't happen, right? Because I mean, square root of 8 is not a, you know, is not a rational number, right? On the other hand, if it's negative 6 minus c squared is negative 2, then negative c squared is 4. C squared is negative 4. This also cannot happen, right? Uh, you can't, the square root of negative 4 is not a rational number, right? So from here, we see that it's not possible. Yeah. And then same thing for the case where b is plus minus 1, d is plus minus 9, right? So I think this one's easier. So because if you are plus minus 1 plus minus 9, then you're basically saying that let's consider both plus, right? You're basically saying that 9a plus c is 0. So 9a equals negative c. So can anyone tell me, when is it true that two numbers, a number is the negative of the other, and it's also 9 times the negative of the other? So what's the only number that can satisfy these, the two properties I underline? It must be 0, but at this point, x squared minus, and then same for the both negative side, doesn't really change anything. So since they're both 0, it just becomes this, right? And now this is much easier because we said that it must be so same for minus. So all you have to do is check this thing that doesn't multiply to whatever we want. So, and x squared minus 1. And sure enough, it doesn't, right? X to the 4th plus 10x squared. So this thing already doesn't match. And this thing is x to the 4th minus 10x squared. So this thing already doesn't match the negative 2 here. So you see, this thing is irreducible. What do you mean? What do you mean by stop? So the c squared equals 8 was for the case where b is B and D were plus minus 3, right? I mean, what about the case B is plus minus 1, D is plus minus 9? Yeah. So yeah, there's no avoiding this. Yeah. You have to argue case by case if you can't use like Eisenstein. So I just did it once to show you the pain. uh, so you all know what to do when you encounter it again. So yeah, we'll go more into field extensions later on, right? We'll go more into simple extensions, and then that's when field theory really starts. Right? Basically, you'll learn quotienting by irreducibles is the same as adjoining roots. You're creating bigger and bigger fields. Okay, I will end it here, and I will see you all Thursday.